Okay, then I would say let's start this online training. Welcome to our online training, RFEM for students, the first part of this series of online trainings, especially for you students. My name is Daniel, and I'm really happy to do this training together with my colleague Praxitelis. Concerning myself, I am responsible at Dlubal Software for the customer support. I answer customer questions as far as possible, as good as possible. And I am also responsible for the marketing, especially for the e-learning platform. So we provide a lot of e-learning videos, provide a lot of content concerning civil engineering, structural engineering, and we are responsible for a lot of videos in this section and this part of structural engineering. Yeah, and together with me is my colleague Praxitelis. Praxitelis, when you want to say something.
Yeah, sure. Hello, everyone. My name is Praxitelis. I'm at Dlubal responsible for marketing and public relations, also for creating online content, for example, e-learning videos and trainings and tutorials. I will be assisting Daniel today. I'm the second voice you will be hearing. I will try to answer as many questions as possible in the chat, so we won't interrupt the training. And the interesting ones, I will tell Daniel to explain it to all of you. So let's jump right in. I hope you have fun and welcome.
Thank you, Praxitelis. Yeah, so as Praxitelis said, we are doing this training very interactive, so it will be divided in different several sections in chapters, and after every chapter, Praxitelis pick out the most interesting questions and we try to answer them as good as possible. Short information about our training tool, GoToWebinar. We are using GoToWebinar in order to do these online trainings. First of all, if you do it, you see it like here. So here you have the possibility to show or you hide this control panel of GoToWebinar, and here adjust your audio settings. So maybe when you can't hear us, please try to change here maybe your boxes, loudspeaker, and here you have the possibility to ask us the questions. Good. Then to the content of this online training. First of all, I will tell you something about the principle of the FEA, so the finite element analysis, or also FEM, finite element method. Then I give a short introduction, especially in the user interface of our program RFEM, and then we will model a continuous plate together. So this will be the introduction example, and then also doing a stability analysis, in this case Euler Case 1. So we will have a clamped column and then a clamped frame. And at the end, you have the possibility to ask us questions. So it will be a nice open discussion together with my colleague Praxitelis. Good. Now I will close now my webcam in order to see more. Yeah, and I see one question, and yes, of course, you will get the recording of this training and also all materials and models will be included in the email. So in the email, you will find one link, and this link will send you to our website, and in the website, you find all information about this training, also the recording and also all models and the materials. Okay, so let's jump in. So first of all, the basics of FEA, finite element analysis. So most of the computer programs are based on the displacement method. Yeah, displacement method is a little bit different comparing to the force method, because here are the displacement, the unknown variables. So the analytical solution of structures, of really big structures, of buildings, is hardly possible. Yeah, for small, simple structures like single beams or continuous beams, it's possible, but the the more difficult one structure get, it will be really hard to calculate it. So what you can do is that you decompose the real structure into a mesh of finite interconnected elements. Yeah. And at every element or of every element continuum, there are properties which will be described at the nodes. And then the mechanical behavior is described by approximation sets. Yeah. Imagine or be sure the finite element analysis is just an approximation of solutions or results. And the most important point is the discretization. So what is a discretization? It's a decomposition of structure into finite elements. This is one of the most important steps doing a finite element analysis. So how looks a procedure of a FEA calculation? So first of all, you determine at local elements the stiffness relations. So you do a mesh of the whole structure, and then you transform the local stiffness relations to the global coordinate system, and then you assembly or you compose the total stiffness relations to the entire structure. And then you have to consider also some boundary conditions, in this case, supports or hinges or something like that. Yeah. And then the program calculates or determines the displacement vectors. And after the determination of the displacement vectors, you can calculate the internal forces and also support reactions and so on. Yeah. Good. So much to the procedure of FE calculation. Good. Now, this will be our first example, the continuous plate. Before we do this continuous plate as an example, I prepared some questions for you. So, first of all, I jump to RFEM, the program, and I want to know from you if you work with two monitors, two screens, because if yes, I will adapt my pace and this would be more helpful for you.
Sometimes maybe we should mention that sometimes it doesn't work in full screen. So if not, just exit the full screen and you should be good to go.
Yeah, thank you for the hint, Praxiteles. That's maybe sometimes a problem, but yeah, this is the solution to the problem. Good. I see most of you have chosen. So I close this poll, show you the results or show me the results, and I see, okay, 1/3 of you is using a second screen, and the rest of you is maybe, I think, just watching. Okay, it's good to hear. I will adapt a little bit my pace in order to have something for everyone. Yeah, and the rest, and I have a second question for you is how many of you or how good is your knowledge in using our program RFEM? Okay, good. I will close this poll, show you the result. And there we can see, okay, most of you or most of the attendees today are beginners. Okay, this is clear because this is also an online training for students, for beginners, really easy basics, and we will do our best for that. Good. So now I want to show you RFEM a little bit. So what you can see here. First of all, I create a new model. To create a new model, you can click here on the file, new, or here also to the white sheet. It's both the same. I click here on new model. And here I give the model name continuous plate. Select the right project name. So in order to save it to the right folder, you can create new projects, new folders, and so on. And what's really important is that we choose the right type of model. Yeah, here we have the possibility to choose one of 4 different type of models, 3D and 2D, and you will see, okay, there are different planes to choose. And for the plate we want to model, we have to choose 2D X, Y, and these phis here, phi X and phi Y, and this is especially for plates who get perpendicular loads. And here, for example, 2D and XZ, these type of model is especially for frame structures, 2D frame structures, or also planes who are getting parallel loads. And this is for plates who are getting wind loads. Okay, good. But we choose this XY profile here, XY type of model. We don't have to choose any classification of load cases. So here we can choose none. So according to standard none. But our positive orientation of the global z-axis is downwards. So, and for those guys who are using different units, here you can change the units and decimal places. Because I use this program here in Germany, I decide to use these kind of units. So yeah, metrical units, meters, millimeters, and so on. And I click OK, and then again on OK, and the work plane will open. Good. So for those guys who are using RFEM for the first time, I want to explain the user interface at an already existing project. So you don't have to do that, just see and watch. So I open here and the project manager, you find it here in the symbol bar. And here I open one example, RFEM, this example. And yeah, so here we see a very easy, simple structure. And according to that structure, I want to explain you the user interface. So here at the top, you find the menu bar. With the help of the menu bar, you have access to all different options, possibilities to model something, and so on. So when you want to add a member or a column there, just go there click on Insert, so the menu bar Insert, Model Data, and then Members, and then you can have that possibility to create different members here. Yeah. The same with loads and so on. If you want to do some calculation parameters, if you want to set some calculation parameters, you find it also here at the menu bar and a lot of other things. Yeah, also some extra tools, tables, and so on. Yeah, and here on the options, so when someone is wondering why I have here the white background and you are using the black background, here you can change it. Here, click here on the options, configuration manager, and change here the white background to the black background. Just double click on the black background in this case, because I'm using now the white background and now I have the black background. But I prefer the white background. So I click back to the white background and I have the white background. Good. Maybe also interesting point, the program options, because we offer here at Dlubal 10 different languages. So we offer English, Dutch, French, Italian, and these other languages. So when someone of you is here, you can switch the language, just close the program and start the program again, and all program settings were changed to the right language. Good. Under the menu bar, you will find the symbol bar. And with the help of the symbol bar, you have a faster and quicker access to the most important functions of RFEM. Yeah. So if I want to create maybe a new single member, just click here to new single member, choose this profile, and draw some members here. Yeah. The fast access to the most important symbols here. Of course, you have the possibility to modify here your symbol bar just with the right click here and say customize, and then you can do, and then you can add or delete some symbols and so on. Yeah. Also with the views, you can change something. So if you like this view and you want to change to the normal isometric view, just click here and the program is shown like that. Okay, now to the navigator. The navigator you will find on the left side. When someone doesn't see the navigator, please activate it here in the symbol bar. And the navigator is divided in 4 different tabs. When I have here the results tab, you will see here a fourth additional tab. But in this case, I want to start with the first tab, so the data navigator. So here on the left side, you see the data navigator, and with the help of the data navigator, you have access, you have an overview of all existing model data. So here in this case, for example, the materials you are using for this project. When I open this tree here, I see materials. I see 2 different materials. First of all, the concrete, and then the steel girder here on the right side. The same with the surfaces. I have an overview of all existing surfaces, and the same also for nodes and so on. When I click, for example, of one node, so maybe here to the 5th node here, and normally it will be selected here in the work plane, but you don't see the node so good because the nodes are very small. So just with the right click here and say find, and then a red arrow shows to the node. Good. And the same also for all other things like cross sections. If you click on one cross section, it will be selected. Good. At the bottom, you will find the add-on modules, short information about RFEM and the add-on modules. With RFEM, you can calculate almost everything. So RFEM provides deformations, internal forces, stresses, support forces, and soil contact stresses. So just these kind of results. But when you want to design something, you have to use our add-on modules. So this is a modular structure of RFEM. So the main basic program RFEM will provide you the normal results like internal forces and support reactions, deformations, and so on. But when you want to design something, so when you want to see how big must be my steel girder, you have to use our add-on modules. Good. But for this training, it's okay when we just focus on these basic things here. Good. Yeah, then jump to the next tab here of the navigator. This is the display navigator. When you want to hide something or when you don't want to show something of this model structure here, you can go here and deselect that. For example, I don't want to see these supports here. I go here and deactivate the nodal supports, and I don't see the nodal supports. The same with the loads. Here I can deactivate, activate them. I have also this kind of function also here in the symbol bar, and the same with the results. Yeah, and also when I don't want to see the FE mesh, I can deselect that and so on. Also the numbering, maybe that's for someone interesting, and so on. Yeah, one tip from my side, use this colors and graphics according to, and here we can choose the cross section. Especially for frame structures is very helpful because when you're using more than one cross section or more than one profile, at normal holes, you're using maybe 5 up to 10 different cross sections. This will be very helpful because you will see now all cross section in different colors. And then you have a really good overview, better overview about your structure. But normally you have this standard, and yeah, concrete is GRU, has the color GRU, and the steel have this blue color. But if you have more different cross section, this kind of information will very helpful. It's very helpful. Good. Then the views navigator. If you are using or if you want to have more different views, especially later for the printout report or when you want to divide your structure in better parts of your calculation, the user-defined views will help you. So, for example, if you like this kind of view very much, click here, create new user-defined view, say, okay, this is my favorite view, click OK. And when you change the view and you want to jump back to your favorite view, just click here to favorite view and you jump back to your favorite view. And the same also with visibilities. So when you want to filter some objects, some specific models, I would recommend really this visibilities to use that. So in this case, I want to show only my columns. So I go here, say members by cross section. I know the cross section of my column. So I open this tree here, activate just the rectangle, and you will see just these members of cross section. Very helpful to do that. The same also with my steel girder here, steel beam. Yeah. And now to the last tab. This is the result tab in the navigator. Here you have the possibility to show you different results. So I cancel my visibility from, yeah. And now I want to show me maybe the global deformation in UZ. So the vertical deformation, I see here, okay, the steel beam, here the plate. Now I jump to the member. So in this case, the bending moment is for me interesting. So I see here the bending moment of the steel beam, also this one here, and maybe also the normal forces. Okay, interesting. Good. So yes, a short information also about the tables. Here in the tables, you find also all information of the models, loads, load cases, and so on, also the results. The one big advantage concerning this navigator on the left side is that you get more information like here in the data navigator. So when I jump to the materials here in the tables and to the materials here in the data navigator, you will see, okay, I have here more information about the materials like here in comparison to my data navigator. This is one big advantage, and you will see it will interact with everything. So when I create something in the tables, it will get automatically the same information here in the data navigator. So you will see in RFEM it's possible to create in different ways to something. Yeah, so not only with the tables and not only with the data navigator, but also with the symbol bar and the menu bar and so on. It's up to you which way of insert or which way of modeling something is your favorite one. It's up to you. Yeah, good. Yeah, and now some information, some short introduction to the movement of RFEM. So with the left mouse click, I can draw a selection window. It depends from which side you begin. So when I go from the left to the right upper corner, to the right bottom corner, I select just the whole things who are really within this selection window. And now watch when I do it from the other side to the top. So from right to the top corner, it will select everything which is not only in this selection window. Yeah, so also this plate and the steel girder. And here's the difference. Please keep that in mind. Also with the mouse wheel, you can zoom in, you can zoom out. I think that's pretty clear. With the right click, you get every time this context menu. So when you click here on the white background, you get this general context menu. And when you click on one of the objects, you will get that context menu of this object or this model data. Good. Yeah, I think that was everything concerning this introduction. Praxitelis, some additional information maybe?
We've got one question, Daniel. Someone is asking, how can we make this adjustment of the units permanent, so it won't change if we close RFEM?
Mm-hmm. You can do it after, you can do it every time. Just go here on the options, and here you will find units and decimal places. And here you can edit your favorite units and cross sections, and then you can save it also. Save as profile, and then when you want to provide that to another engineer or to another person, user who is using RFEM, he can load this saved profile of these units here. Okay. I think
Okay.
that was good.
Mm-hmm.
Yeah. Then I have prepared for you 2 questions. So first of all, this one. Good. Most of you have already chosen, so I close this poll here, show you the results, and say also the right answer. So most of you were correct. So what is a discretization? It's a decomposition of structure into finite elements, and this is the right answer. Okay, and the last question for this chapter is this one. Okay, I close this poll. And again, the most of you were right. RFEM is a 3D FEA program for calculating members, plates, and shells, not only frame structures, but also members, plates, shells, folded plates, solids, contact elements, and so on. Good. So let's begin with our example. So for that, I jump back to our example, continuous plate. And the first step I do is modeling our continuous plate. So first of all, I want to show how it will look like. It will look like that, yeah? We will model 3 different surfaces, and then we compare these results with our member, so with a continuous beam. And when you see, we will discretize it in different meshes. So we will have different different sizes of FE meshes, and this will be very interesting how the different results will interact. Okay. Good. So first of all, I create a rectangular surface. So for that, I click here, I go to the symbol bar, go here and click on rectangle. And here, first of all, I modify the material. I click here on edit material, or if someone doesn't have this concrete C3037, go here, edit material, and open the material library. And here you have the possibility to choose to select one of a lot of different materials. In this case, I decide taking this concrete. I refer to the normal concrete and to the Euler Code standard. Yeah, I choose the concrete C3037. For the international people there, what does it mean, this C3037? This means that we have a characteristic cylinder compressive strength of 3 kilonewton per square centimeter and also a cube compressive strength of 3.70 kilonewton per square centimeter. Okay, I click on OK. One important point is that we set the Poisson's ratio to 0. In order to have no impact from shear deformation or additional shear deformation. Click here on OK. And then we set our thickness of our plate to 300 millimeters. Click on OK. And then we draw our surface 10 meters long and then 5 meters into the opposite global Y direction. Yeah, and for the training, we do the same again, exactly the same again. So again, click here on new rectangular surface. Click just on OK because all information are right. And draw this rectangular surface again, 10 meters long and 5 meters high or wide. Good. And then I want to show you one big advantage is now we want to copy it. So select everything, draw a selection window above the over the whole surface. Now click here, have the right click to the surface and then say move copy. So, and here we say, okay, number of copies should be 1 because we want to copy it, of course. And the displacement vector should be from there to there. So now we have two possibilities to enter here a value of -10 or that we can pick the displacement vector, and I want to show you this option. So select 2 points and return displacement vector. I click on that, say from there to there, and the displacement vector was created automatically. Okay, click on OK, and voila, you will see this were copied. This was copied here, exactly 10 meters higher. Good. Now I want to have the additional continuous beam or a beam. So I want to move these 3 surfaces a little bit. So draw a selection window over the whole 3 surfaces and grab the middle surface here at the left in the left bottom corner and grab it from there to there. Yeah, good. The next point is the creation of the beam there. I go here, create new single member. So in RFEM, is it like that? When you want to create columns, beams, girders, braces, and so on, you have to create members in RFEM. I click on that, and because we haven't created a new cross-section yet still, we have to create a new one. So go here, create new cross-section for member start, and then you have the possibility to set your cross-section properties, for example, manually, but of course you can choose one of these already providing cross-section. Here I decide to take this rectangle cross-section. So I enter the value of the width, 1000 millimeters, because I want to relate also to our concrete surfaces here, so concrete plates, and the height is 300 millimeter. The material is the same. I click here on OK. And again, I click here on OK. And I draw my member from there to there, also 10 meters long. Good. Now I pressed the Control key on my keyboard and also the mouse wheel, and I rotated and I rotate my view of RFEM. Yeah. Now I can see also a little bit 3D. Okay, good. So in order to provide or in order to calculate it like a continuous plate or continuous beam, we have to divide it also we have to divide it because we need an additional line there in order to provide the line supports, and also here an additional node in order to provide an additional node for the support, nodal support. So how we can do that? Here we have the possibility to divide this line. Click on one line with a right click. It will open this context menu, and here on divide line we have three possibilities: graphically, by in intermediate nodes, or by distance. I decide graphically, and here I have the possibility to set the steps. Yeah, in this case 0.5 meters are enough. And then when I go over one of this line, I try to divide it at the length of 5 meters. Yeah, you will see when I go through this line, it will change also. It will appear the right value also in the left window box. In this case, I have now x 2 meters, and here, for example, x 8 meters, but we need x 5 meters. Yeah. And that you can, and this is one thing or one big advantage, you can do this at every line. But in this case, it's okay when we do it only for this bottom line here. And you will see, okay, now we have two lines and an additional node. And now with the additional node, we can draw a line. So go here to the symbol bar, click on new line, and draw this line perpendicular to the other side. Okay, this is one cool thing. And the same thing we do also with the middle surface. Right click on the bottom line or the lower line, then click divide line, but in this case we want to do it by distance. None. Now, really important point. When every line and every member has orientation, has own orientation. So what does it mean? You see here now these kind of arrows. These arrows symbolize me that the starting node is here on the left side and the ending node of this line is on the right side. Yeah, this is very, very important when I use this divide line using distance, because here I can set, okay, from which length or from which distance should RFEM go to divide this. So when I set here 6 meters from the line start, it will be, then this new node will be created at the length of 6 meters from the line start, or from the line end 4 meters. Yeah, it's very important to know that we have here in RFEM this line orientation and also this member orientation, and depending on the orientation of these arrows, you will see where is the beginning and where is the ending of this line. So in this case, I want to divide it also exactly in the middle, 5 meters, and you will see it here. Okay. Now, one cool point is that we can copy one object or several objects, also a lot of other objects with the help of a really nice function. And this is per drag and drop, via drag and drop. So I click on one line, then press the Control key on your keyboard, and then the left mouse click, and drag and drop it from there to there. Yeah. The same thing we will do for this other thing. Yeah. Really nice thing. So again, press the Control key, click on the object you want to copy, and draw it or drag it from the favorite place you want to have it, and then left the mouse click, and yeah, then you copied this thing here. Good. Now, last thing is that we want to have here also an additional node. Here in this case, I want to divide it in another way. And the first difference is that we don't have here a line. We divide member. In this case, in intermediate nodes. So when I want just one additional node, I have to create here, I have to set here it as 1. And this member will be divided in 2 same long parts. Okay, when I have here 2, then the member will divide it in 3 same long parts, and so on. Yeah, exactly in the half, and now we have it. Good. Now we have to set our supports. For that, you can create here in the symbol bar new line supports. I click on that, and we leave this option hinged here. Yeah, so please choose the hinged. When we go here, create new type of line support, we see, okay, these support conditions are setting that we are transferring just vertical forces. Use that. Click on OK and choose the lines here. You can also draw a selection window, but consider that you do it from the lower part to the upper part, also from the right to the upper corner here, like that. This is possible. Good. Now the same thing for the beam. First of all, I choose or I select these nodes here. Doesn't matter if I have also this member chosen. I go here again to the new nodal support. And here I go again to the new nodal support. And now I want to say you something about the support conditions. When I activate here one of these displacements or restraints, this will mean that the displacements in this direction are blocked. Yeah. So in this case, UZ is blocked. This will provide us a support reaction, support forces. In this case, vertical support forces, because we are blocking the displacement into the Z direction. You will see it here also in this bitmap here. And keep that in mind that when you want that the support node is carry these vertical or horizontal forces, then you have to activate here this one. Okay, good. I click on OK. And now one important point. In order not to have here some torsional forces, we have to activate an additional restraint here. So I have to create a new type of nodal support. I have to activate this Px because I don't want to have some torsional movements around the global x-axis. So I have to here x. I have to activate here also Vx. Click on OK and click on again OK. Yeah. Then it would be possible that the beam here could deform around his own axis, and this wouldn't be helpful. And this wouldn't be good because then we would get an error of the calculation of RFEM. Okay, good. So next thing is adding loads. Yeah. Before we add some loads in RFEM, we have to define first of all some load cases. What are load cases? Yeah, load cases can be self-weight, imposed loads, wind, snow loads, and so on. In order to do that, we click here on new load case. And here we see different action categories, also the load description. And in this case, it's okay when we write here just test load or something like that. Yeah, doesn't matter. In order to compare the results better, I deactivate the self-weight. Yeah. And click on OK. Good. Now I put there some loads. In this case, the new surface load, because we have here 3 different surfaces. I click here on new surface load. I refer to the global related to true area. My magnitude is 10 kilonewton per square meter. I click on OK and choose my surfaces here. The same thing I do for the member. For members, I need member loads. In RFEM, there are also some line loads. Please keep that in mind. There is a difference concerning these two ones. Member loads are really just for members, like here one, like here, this is a member, or frame structures. Here you have also members, so please use the member load. But if you want to put some loads on edges of some surfaces, then you have to use line loads. For example, when you want to consider here some wind loads, yeah, then you have to use line loads. Okay, good. Here in this case, I use member loads. I click on that. My load parameter is 10 kilonewton per meter. And I draw here as my select jointer. Good. Almost done. Now I don't want to show the loads, so I click here on this eye here with the loads. I deactivate the showing of the loads. And now I want to do a discretization. So I want to have different sizes of FE meshes. One bigger, one in the middle, one smaller. And here we leave it like that at the member. So here in the navigator, data navigator, you will find the different FE mesh refinements. So click with the right click on one of the FE mesh refinement and say new FE mesh refinement. Here you have the possibility to relate or to apply to the surface. And here, please enter the value of 1 meter, target FE length 1 meter, and choose the right surface. So I click here, choose this surface, click on OK, and then again OK. And this FE mesh refinement will appear here. It is symbolized by this, by this quadratic window here. And the same thing we are doing for the other surfaces too. So again here, right click, new FE mesh refinement, select the right surface, and enter here a value of 0.5 meter. And here the same thing, but we can do it also in a different way. Right click, FE mesh refinement, new, number is already right. Click here and put there a value of 0.1 meter. Okay, good. Next thing are sections. In order to see the results in an integrated way, we need sections. For that, I create 3 different sections for the plates. So here, right click here in the data navigator, you find these sections. With the right click, I want to create a new section, give them a name, in this case, AA. The edge points of sections I will choose. So I refer from the one end to the other end. I refer just on that surface. And the section on surface, or the projection direction, should be in the global set direction. Good. I close this with OK. The section was created. And this kind of step I will do for the other surfaces too. So again, click here on new section, in this case BB. Provide here for this one. And also the third section. Okay, good. Now we have everything. Now we can calculate it. Yeah. So for that, you can click here on Calculate All or here on Show Results. Same thing. When I click here on Show Results, this window will appear and results from load case 1 not found. Start calculation. Okay. Okay. And first of all, what you see is always the deformation. And first of all is check the deformation if it's okay. And yeah, the deformation looks okay. Here at the member, you will see also deformation when you want to have it a little bit in a better way. So the way of showing that, go here to the display navigator and click here also to deformation. Go to members and say, okay, the cross section should be colored, and you will see now also the coloring of the deformation of the cross sections. Okay, good. Now, first of all, how we can do, how we can prove our results. First of all, I want to activate the sections here, and I refer to these kind of basic internal forces. And I activate also these members here, bending moments. Okay, what we can see now. So, first of all, we see here the bending moment, first of all, of the member. I think that's pretty clear. We have here field moments, then we have here this negative moment, and here also the same thing. And now, very important point, there are different FE mesh sizes. Yeah, here we have this 1 meter discretization, here 0.5, and here 0.1. And you see, okay, the bigger one FE mesh size is, the results aren't so exact like here at the very fine FE mesh sizes. Yeah. So here at every 0.1 meter, one result is provided. Here on every 0.5 meter and here at every 1 meter. Yeah. And please keep that in mind. It's up to you how you will do that. Because here, look at this one. Look at this here. Look at this distribution here. We have here linear things. And when you will compare these kind of results with that one, you will get different results. Yeah, the results at the specific points, like here at the middle, so here at the line supports, are very similar. But when you compare the results, maybe at 1 meter here, 1 meter away from that, you will get definitely different different results. Yeah. Good. This is interesting thing. Yeah. And maybe someone of you is asking, okay, why are the internal forces, here in this case, the bending moments, why are they a little bit different in comparison maybe to my hand calculation? Yeah, because in our study, we use our hand calculation. Maybe someone of you is some formula in order to get that. And normally there should be maybe, some nicer values, I would say. Yeah, so not here this 31.80 kilonewton meters, but 38.25 kilonewton meters. Yeah, I can tell you where's the difference. The difference is you considering the shear deformations, because normally Here in RFEM, when I go to the menu bar calculate, go to the calculation parameters, you see here the activation or the activation of shear stiffness of members. What does it mean? Normally, you have also in the reality shear stiffness of some structures. And here in this case of the members, RFEM consider that. And when you do some normal hand calculation with the help of some formula, you don't consider that because you calculate it very stiff, so no, without any shear stiffness, because the hand calculations say you have endless shear stiffness. Yeah, so infinite shear stiffness, but in reality you have some shear stiffness, and so RFEM calculate that also with the consideration of shear stiffness, and this is also the reason why you get there different different results. Yeah, so please keep that in mind. So now watch out when I deactivate that. Watch out the result of the member. I calculate it again. And you will see the different result. Yeah. Now you have the same result in comparison to your hand calculation. And yeah, when you want to compare your results with your hand calculation, please keep that in mind that you have to deactivate the shear stiffness here in RFEM. Good. So much to that. Praxitelis, are there any questions or should we mention something out, strengthen something?
Yes, Daniel, we've got two questions. One is, according to what do we choose the number for the FE mesh refinement?
Mm-hmm.
Or the scale, let's say so.
Okay. Yeah, it's just simplification, I would say, to show you different FE mesh sizes in order to show you how that different FE mesh sizes will react to different results. Yeah. If you have two big FE mesh sizes, you will not get not so good results. Yeah. And if you have very fine FE mesh refinements, like here, you will get very good results, but the program needs more calculation time. Yeah, will calculate longer. And normally, at least there should be, in order to have good or normal results, there should be in one surface at least, so from there to there, at least 4 FE elements. Then you get normally results, they are good enough. Yeah. So when I deactivate that, show me just the FE mesh. Because you will see, okay, you have here 1, 2, 3, 4, 5 FE elements. This is okay. Yeah. But better it would be when you have more than that. Okay. Next question, maybe.
We've got the question, what is the difference between line load and member load?
So you have here a member, yeah, this continuous beam. This is a member. In order to add some loads there, you have to use member loads because member loads are referring really to members. But when you want to put some loads on a surface, on the edge, for example, yeah, this isn't a member, so you have to use a line load, yeah. When you want to consider maybe, now I have to look it up, this word. Sorry for that. When you want to consider a railing or a handrail, so maybe I show you a picture of that. Yeah, when you want to consider something like that, yeah, with the help of some loads, then you have to put their line loads, okay? And this is the main advantage, main difference. Okay. Another question?
No, I think we've covered everything.
I see one question.
Oh, okay.
This in my output bending moment diagram is not visible. Which option do I have to activate? I think that you've forgotten to activate the sections here. To activate the sections here, and also here to show you the results. Here in the results navigator, just activate the sections and show results values and also show generally the results. And here for the members, you have to activate the members here and MY. Okay. And the last question is, at the result, can I change only the orientation of shear forces without changing the orientation of bending moment? I understand. So here you want to have, here you see the shear forces and you want to change maybe the direction, I think. Yeah. I don't know if that's possible, but you can change the orientation of the member and then we will see how it will influence the shear stiffness, the shear forces. So select this one, say member orientation off, then you see here this member orientation. Right click and say reverse member orientation. Then you have to recalculate it. But yeah, the shear forces are now on the opposite side, of course. But the bending moment is on the right side. Because when you want to see maybe the tension, don't know how to say it. Praxitelis, do you know the word for Zugfaser?
Wow.
Bottom fibers, maybe? I think this
Tension.
is one.
Tension fiber?
Tension fiber. Okay. I found it. So when someone is looking for the bottom of the tension fiber of a member, you can find it here in the display navigator. Go to the model and activate the bottom fiber, and here you will see this fiber or the tension fiber of the member. It will helpful also for the study. Yeah, good. Good. Then I would say I have some questions for you. I have only one question for you. Better for you. Please answer me that question. Okay, good. Most of you have chosen. I close this window, show you the result. Yeah. What happens if the shear stiffness is activated? The right answer is the first one. Shear stiffness or shear deformations are considered. I think that's clear now. Good. So now I jump back to my PowerPoint presentation because I want to show you some theory about the plate theory. So in the study, you learn, first of all, the beam elements, so the normal beam theory, the calculation beam theory. And normally it is like that you learn the normal Bernoulli beam theory. So, but there's also opposite of that. It's the Timoshenko beam. So what is the Bernoulli theme? So first of all, there is the cross section. When I deform something, they remain in plane, and the cross section remain also perpendicular to the member axis. Yeah, I have also prepared a picture later for that. And one important point is that we don't consider any shear deformations because our shear stiffness is also rigid. Yeah, this is one thing you study. Yeah, you will calculate in the study. You will start with that because it's easier to consider that, to calculate it. And also a lot of formula you use, they are similar to that. Yeah, good. But there's also the Timoshenko beam. And the Timoshenko beam, they are the same things like here, the Bernoulli. So the cross section remain in plane and so on. But you consider shear deformation, and also the shear stiffness is limited. So it isn't rigid anymore. So we get an additional shear deformation. You will see it here, okay? This WQ and also more deformation. So here we see, okay, it remains in plane, perpendicular to the member axis. And here at the Timoshenko beam, we see, okay, we get an additional angle, in this case, and this is a gamma angle, so additional deformation. So this member theory, this beam theory, we can also transfer to the plate elements. So on the left side, similar to the Bernoulli beam, you have the Kirchhoff theory and also the Reisner-Middlin theory for the Kirchhoff theory. So here's some information, what we are referring to what. So we have geometrical linear. This means that we are looking just for a small deformation and linear elastic material law. So we are using this Hooke's law, and the cross sections remain flat. So we have no warping, and also the constant thickness. And also here, no consideration of shear deformations. Reisner-Mindlin, the four things are the same, but similar to Timoshenko, we consider shear deformation, and we consider also transverse and lateral strains. What are transverse and lateral strains? So imagine you have here a beam, and you tie this beam with the help of some tension forces, and along his length, it will get, looking at this cross section, at his width, but also as well as his height thinner, and this is the transversal lateral strain. Here also with this mu factor, it will provide this lateral strain here. Okay, good. Back to the plate theory, where we transfer to the plate elements again. So Kirchhoff, as a summary, no consideration of shear deformations. So when I calculate with this Kirchhoff theory, these results are good enough for thin plates. Thin plates are normal concrete plates you use in the normal building structures and so on. So and you are considering just pure bending load bearing capacity. And this is also only a simplified approach. Otherwise, to the Reisner-Mindlin, here the results are good also for thin plates, but also for thick plates. And the component of the shear influence is relatively high. So you have to consider these kind of shear deformations. And when we would neglect these shear forces, the errors and the bad results would be very high. And that's also the reason why we have a higher value approach, and we get more accurate shear forces. So as a summary, Kirchhoff you can use just for thin plates. Thin plates are normal concrete plates and so on. And Reisner-Mindlin you can use also for thin plates and for thick plates. And my recommendation for you is, please use always Reisner-Mindlin, because then you don't make any mistake. So let's look also to RFEM where we can do that. So here under the calculate menu bar, you will find these FEmesh settings. The calculation parameters. And here you find the different plate bending theory, Mindlin and Kirchhoff. And now, remember these values here. I choose Kirchhoff, calculate it again. So, and here you will see now the different results. So there's a difference. And the greater the thickness of one plate is, the greater is also the difference between these two calculation theories. My recommendation for you, please use Reisner and Mindlin. Then you are always on the safe side. Good. Now, let's jump to the next example. And this is the Euler Case 1 and the stability analysis of a frame. So in the study, you learn also the stability analysis a little bit, buckling cases and so on. And for sure, also the Euler cases. And we want to have the same here also with RFEM. So what we do now is modeling this first column here with an clamped uh, support here, and the same also with this frame after that. Good. Now I would say let's go ahead and do that. So for that, please create a new model. I create here a new model by clicking here on new model here on this white sheet. I write the Euler Case 1, put it here to the examples, and now important point is here the type of model should be 3D, please, because we want to consider both directions concerning the buckling, figures, pictures. So I want to activate here this 3D type of model, and my z-axis is orientated downwards. Yeah, one of my projects are already existing, so I write there. Yeah, good. I have to take a sip of water. I'm a little bit thirsty. Good. So, as I said before, with RFEM, you can calculate not only plates, surfaces, and so on, but also frame structures. So, we want to do that. So, in order to do that, go here, click on New Single Member. And here I have the possibility to create a new cross-section. I do that. And because I am from Europe, or better, I'm from Germany, it's very common that we use here our HEB profiles. Yeah, so I click here on one of this HEB profile. When you don't have it here, click here on the material on the cross-section library. It's the same. Choose one of the rolled cross-sections. And choose here HEB profile. There's a wide I-beam with there's a wide I-beam, sorry, with parallel flanks. So here we have our flanks, here the web is especially used for transferring a lot of bending moments and also compression forces. And we choose this HEB profile 300. Click on OK. Again, I click on OK. And now I want to do this column 10 meters high. So, and now you will see I have a little bit problem because I use now the work plane in YX. You see it here. Here I have the different work planes now, but when I want to do that 10 meters high, it will not be possible because I referred also to this flat plane here. So one possibility is to change the work plane, like here. I can change the work plane and now I can draw my column 10 meters high. This is possible. But there's also another smarter solution, in my opinion, is that I set the length and direction. So here I have this window. I set the length and direction perpendicular to my work plane. Set here the length, should be 10 meters high. And you will see here now also this member here, but not to the positive Z direction, but into the opposite Z direction. I refer to my origin node here and click on OK. Now you see here this member. So, and now I want to add some supports here. So I select here the lower node, go to the symbol bar, click on New Nodal Support. And here I activate rigid. So all constraints and all displacements, all rotations are transferring to this support. You can see also here these support conditions. Yeah. When I have activated everything, it will look like that. Okay. But in this case, it's okay when I just activate here or I choose this rigid support here, click on OK, and this rigid will appear here. Good. Now, next thing is putting there some loads. So in order to do that, we have to add some load cases again. And yeah, for that, I click here on New Load Case. I don't consider the self-weight. Just click here and test load. Doesn't matter what's the name of this load case is. Just put the load description and click on OK. Good. Now put there one new nodal load, so a single force. Enter here a value of 10 kilonewton. Click on OK. And this was the wrong node. Please draw it from there to there. Okay, I made a mistake, unfortunately. I want to add this single force here to that node. Just click here, new node load, put there a value of 100 kilonewton and refer to this node here. Good. Now, one important thing. Normally, the program calculates it by the theory of first order. So when I look to the results, I change a little bit my view in order to see this a little bit better. So here, go on view, reverse in Y direction, and I see it here. So the displacement, the deformation aren't interesting for me now. For me is interesting the bending moments. So I have no bending moments. I think that's pretty clear. Now I add a horizontal force in the global X direction. So I put the 10, click on OK. I calculate it again. And then you will see, okay, now I have a bending moment. I think that's pretty clear because I have a lever arm of 10 meters, a horizontal force of 10 kilonewton, 10 multiplied by 10 is 100, and a normal force of 100 kilonewton. In this case, compression force because it's negative and so on. Good, I think that's pretty clear, yeah? But in RFEM, we have the possibility to choose different calculation theories. So I go back, open the load cases and combinations. And when you go to calculation parameters, you will find the method of analysis. And normally the load cases are calculated by the geometrical linear analysis. But you have also the possibility to consider second order analysis. Maybe someone knows this under the name P delta, yeah? And I want to show you the different results concerning that, because in Germany we have the second order analysis and also the geometrical linear analysis. And when you consider that these two kind of calculation theories, there are some differences, yeah? And I want just to show you the differences. When I activate this second order analysis, so first of all, we have compression force of 100 kilonewton and also an bending moment of 100 kilonewton meter. Yeah, I think that was pretty clear. Now, with the help of the second order, you make a calculation after, so you make the calculation, so you see the equal systems on a deformed structure. Yeah. So I calculate this again. And first of all, I want to show you the horizontal displacement. In this case, UX. Remember this 68.7 millimeters. When you multiply this with 100, you will get an additional bending moment, yeah, of 6.87 kilonewton meters. Now look to the bending moments. Here we have a total bending moment of 106.87 kilonewton meters, because with the help of the second order, because there we make the equality. I have to look it up, this word. Okay, yeah, Google Translator is not so good. You build the equality, the equal system with the help in order to get your support, internal forces, and so on, the support directions at the deformed system, and at the second order, yeah, or P delta. And when you have just the geometrical linear analysis, you calculate this thing in the undeformed structure and also get these results at the undeformed structure. And here we have the second order, so the P delta, and therefore you have additional bending moments due to this horizontal deformation. This horizontal deformation multiplied by this vertical force will provide you this result at the bending moment and provides you additional bending moments. Yeah. So I want to show you that in different windows, maybe. Sorry, this one. So here I have the bending moment. Here I have the normal force, and here I have the shear forces. And when I look now here to the horizontal deformation, you will see, okay, this deformation multiplied by the by the vertical force will provide me an additional bending moment of 106. Additional bending moment of 6.87 kilonewton meters, and the normal bending moments are this horizontal 10 kilonewton multiplied by the lever arm of 10 meters, and this will provide me this bending moment. And this is one thing I want to mention because I think this is very important also when you use RFEM, especially when you use this second order. Good, so much to that. Good. Now we want to make a stability analysis. I put this horizontal force away. So I write the 0. I just have this vertical force. And now I want to make a stability analysis. What does it mean to make a stability analysis? I want to see different buckling cases and also to see the critical lengths. So I have to start one of my add-on modules, in this case RF stability. RF stability, when I open this, it will open this window here, and RFEM stability is make a stability analysis by the eigenvalue method. So it will provide critical lengths, also critical values for this calculation of stability. So for that, I want to have this lowest eigenvalues. Number of eigenvalues should be 4, not more. I refer to this load case, test load, and I want just to consider this. I don't want to consider, and I don't have also to activate minimal initial pre-stress. But one important thing is that we activate the division for straight members. So I added the FE mesh settings for members, and there I have to modify it to 10. So the minimum number of member divisions should be 10. I click on OK. And now I click on OK just because my load case, I forgot to change that. My load case should be calculated by the geometrical linear analysis, not by the second order. I explain it to you later. So now I open RF stability again. Now I can calculate it. And the first things you can see is on the left side, this critical load factor, and on the right side, this magnification factor. The most important thing is the critical load factor. What does it stand for? This critical load factor says to me that I have to multiply the whole loads of 100 kilonewton by this factor in order to get an instability of the whole structure. So when I get this instability, the whole structure wouldn't calculate and will collapse. Yeah. So when I have this 100 kilonewton and I multiply this 100 kilonewton with this factor of 4.4, so I get a vertical force of 440 kilonewton, and I calculate it with the help of the second order. I will get an instability of the whole structure, and my structure would collapse due to this critical load factor. Yeah. The magnification factor says to me with which factor I have to calculate. I have to multiply the bending moments in order to get my bending moment after the second tier, to get my moment in the second order. Good. Now to the effective lengths and critical loads. Here you see again this critical load. These are the 443 kilonewton. When I have more than this one, my whole structure would collapse. Yeah, I will get an instability, and my program wouldn't calculate that. Yeah, and here I see also the different effective length factors and also the effective lengths. These are these buckling lengths here. So when you consider this Euler cases, because we have here Euler case 1, we have here also this effective length factors of 2. Maybe someone of you asking or wondering, okay, why isn't it exact 2? This is also due to this shear stiffnesses. So, but first of all, let's look to this effective lengths and to the buckling cases, to the different eigenvectors. So I click on graphic, and here I see the first eigenvector or eigenform. And when I want to have this a little bit nicer, this view, I go here, go to the display navigator, and say, okay, here are the results. I want that the members have colored cross sections. And I think now you can imagine it a little bit better. So when I have here vertical forces, just a single force, what is the first eigenform of this cross section? I think that's pretty clear. The first eigenform is, or the first buckling is, that the profile is buckling around his own, around his weak axis. And this weak axis is around his z-axis. I activate it here. I click on that column. I click here on local axis of members on, and here you see the local axis. So I have here the y-axis and the z-axis, and along his length I have this x-axis. And the first buckling case is that this column here buckles around his weak axis. And the weak axis in this is, in this case, the z-axis. I think that's pretty clear because my flanks are here in this direction. They shows in the global x-axis, and the weak axis is in this direction. I think that's pretty clear. When we jump to the next eigenvector, the second, this is a buckling around his strong axis. Yeah, I think that's pretty clear. Here I have my flanks. This is the strong side. And here I have a critical load factor of almost 30. This would mean that I would multiply my 100 kilonewton with almost 13, then this would collapse around his strong axis. Yes, and also some other eigenforms and so on. Good. Now I want to show you what happens when we have more than these 443 kilonewton. So we have 100 kilonewton. We activate the calculation parameters calculated by the second order analysis, so the P delta. And now we put there more than 443. In this case, 444 kilonewton, and we will get an error. And we calculate again. Yeah, and there is the error message. The stiffness matrix is singular. The model is unstable. Instability found in FE mesh number, and so on. Yeah, and there is a possibility how you can do that. Yeah. So This means that we have too much load on our structure. Good. And now when I put there 443, it would calculate because this is under our critical load. Now when I jump to the RF stability, sorry, I have to calculate everything. I open RF stability and you see my critical load factor is now 1.001. Yeah. Okay. Some short information about this critical load factor. If this critical load factor is under 1, yeah, so 0.9 or 0.8, then you will get an error message when you calculate your structure by the second order. Yeah. And yeah, and if you have here values of critical load factors between 1 and 10, you have to consider a calculation after the second order, and everything over 10 is okay. You don't have to consider any second order. It's when you calculate in the Euler Code 3. So Euler Code 3 are there you calculate steel structures. There you have to consider that. Okay, good. So much to the critical load factor. Good. Praxitelis, are there some questions?
No, Daniel, no questions yet. So I think we can carry on.
Okay, good.
Mm-hmm.
So I have prepared 2 questions for you. First of all, this one. Okay, good. Let's see this result. So, of course, the plate theory of Kirchhoff considers no shear deformation. The plate theory of Reisner-Mindlin does. And another question is that one. Okay, good. Most of you have chosen. I close this poll, show you the results. Of course, the critical load factor says, okay, which factor can I use to increase load until my whole system will fail? Good. Okay, so the last example of this online training is modeling 2D frame structure. I show you here again this one. Okay, good. For that, I copy just here this column. So I draw a selection window of that. Right click, say OK, move and copy. Number of copies, 1. And the displacement vector should be 10 meters to the X direction. Click on OK. I deactivate the member axis now because I think that is clear now. And now I can change the height of this. I can change the height of this columns here. When you want to change something afterwards, that's every time possible. Like here, for example, I want to change the height of these columns. I select the upper nodes here, click on right click on one of these nodes. Yeah, sorry. Click one of these here nodes, say okay, edit node. And because the nodes have the same coordinates, the coordinate Z will appear, and here you can change it now. And we change it here to -6 meters. I click on OK. And now I want to model a girder from there to there. For that, I decide to create a new cross-section. So I click here on New Single Member. I create here a new cross-section for the member start. And I take this IPE profile. IPE profiles are very popular for using for using especially as girders and beams when you get a lot of bending moments, because they are very cheaper to produce than these bigger HEB H profiles here. Okay, I choose here this IPE 300 profile, click on OK, click again on OK, and draw this girder from there to there. So from the left side to the right side. With right click or escape, I close this window, and I have here now a frame. Good. And I look back to my load case. So I jump there to the load case, and I copy now this single load from one corner to the other corner by pressing by drag and drop. So again, I click on one of this, I click on that single force, press my control key on the keyboard, and copy it from the left side to the right side. Now I want to change the values, so I select them by drawing a selection window from the right to the upper left side. Right click on the force, click on edit nodal load, and here I say, okay, I want to have 100 kilonewton. Okay, Now I say again, okay, calculate all, please. And now we look to the different buckling cases. Okay, now jump back to the RF stability. And here we see the first eigenvector, the second, and the third, and then the fourth. Okay, so what we can see now. The first one is out of the plane. We can make the factor a little bit bigger, the displacement, the display factor, yeah. So the first buckling is out of the plane. The second also. And when you compare it to real structures, this shouldn't be possible. This is one of the main things. We as structural engineers, we don't want that that frame should have this buckling case, because this is not very good. And that's also the reason why we have there continuous beams, yeah. And these continuous beams will hold this whole structure, yeah. I can show you that also to a real hall, for example. I click here and the project manager. I have maybe there somewhere a nice example. Yeah, for example here. And yeah, in order not to have this kind of buckling case, we have here also this continuous beams here, and they will hold this frame here in one plane. Yeah. But here in this case, we don't have this. Yeah. And this is also the reason why this will fail at first. This the third eigenvector is that buckling case or that eigenform that's very familiar, because this is maybe something what we already seen maybe in our study or something like that. Yeah, I think that is pretty clear. And in order to get this as the first buckling case or as first eigenvector, we have to consider the right boundary conditions. So we can add there some additional nodal supports, and then we don't have this kind of buckling form or eigenform. Yeah. So let's do that. I take new nodal support, and what we have to do now is that we don't allow any deformation in the y direction. So I click on new nodal support, click here on new type of nodal support. I activate only the UY because I don't want to have any deformation in the y direction. So I have to activate this UY. I click on OK, again on OK. I select this node here. I select this node here. And now watch out what we have now for eigenforms. I calculate everything. Yeah. And now my first eigenvector is this one I wanted to have. So I think this is pretty clear now. But now you see, okay, I have again some buckling forms out of the plane along this column. Yeah. So in order in order not to have this again, I can change the system from 3D to 2D to 2D. I show you the difference. So go to data, go here to the data navigator, to the right project, click the right click on general data and change that type of model to 2D XZ. Then this window will appear and you say, do you really want to change the type of model? You say yes. And now you have just this one plane and also this boundary conditions are a little bit different because now it can be possible that this frame can deform out of this plane. So let's look to this RF stability again, to the results. No support of restraint, no problem, because now we have done the any supports at the node. Yeah. And now we have here the first eigenvector and the three other ones are just in the plane. Yeah. This is something you have to consider. Good. Yeah. Praxitelis. I think I am at the end of this online training. Do you want to add some information or do you want to mention something?
Yes, Daniel. Okay, as we've got no questions. I would like to show that context menu, maybe show them how it works when we draw a selection window over an element.
Do you want to show you that or should I show
Oh,
that?
yes, of course, I can do that. Yeah, sure.
Okay. So I give you the rights to do that. So let's skip the screen.
Okay, so do you see my screen now?
Yes, we see your screen.
Okay, perfect. Okay, so I would like to show you that little to give you a little tip here. When we draw a selection window like this, for example, and then right click, you can see here on the context menu all elements that are selected in this window. So if we, for example, want to edit only the nodes, you can go here to nodes and click edit. So now you can edit all these nodes that are selected in that window at once. I could show maybe Daniel the new flight mode maybe as well.
Yeah, of course, show that.
Okay, so we've got a new super cool feature which is called flight mode. You can press on your keyboard Shift plus F, and now with your mouse you can rotate, and with the arrows you can fly through or walk through your model. I think Daniel, you can adjust the pace too.
Of course, you can adjust the pace
with the plus and minus, or was it
plus and minus keys? Yeah.
exactly? Okay, so you can adjust your pace with plus, for example, make it faster, and fly or walk through your model if you want to see something. Okay, and maybe the clipping tool as well. You can go here under if you got any results, for example. Let me show you this real quick. My loads are in German, but that's another problem, I think. Okay, so if you got your results here on your model, you can go here under, where was it, Daniel? View or?
Yeah, insert.
Insert. Exactly. On your clipping plane. And now you've cut through your model, and you can see your results at that exact line, that exact cut. And of course, you can adjust here the offset or the step, make it bigger, for example. And of course, the angle too. Change here the plane or XY, for example, and view your results. Okay. Anything else, Daniel? Maybe I could show?
No. So for the attendees, when you have now some questions, please write your questions. I have now time to answer all of these questions. And yeah.
By the way, this is the model which we will show in part 2.
Exactly.
We will show you step by step how to model it and put loads on it. And yeah, this will be a good guide, I think, to your first steps in RFEM.
Exactly. Good. I switch to my screen now, Praxitelis.
Yeah, sure.
Good. Okay.
We've got some questions. Will we be able to rewatch this webinar?
Yes, of course. We will post it on our website, and you will get, after this online training, an email. And in this email, you will find the link to the recording and also the link to the materials and models, and also a certificate concerning this training.
And we've got another question too. How can we calculate the buckling length using the stability module?
Concerning the buckling length, I show it here again. So open the RF stability analysis, go to the program, and here at the area of effective lengths and critical loads, you will find the different members. So here in this case, member number 1. And when you go and look to the right eigenvector number, you will find the effective lengths. And these are also the different buckling lengths. Yeah. And when I do it again with this Euler Case 1, here we have normally a buckling length of, okay, this is now 6 meters multiplied by 2, so the double time. So we have a buckling length of 12 meters. I calculate it again. Sorry, I have, okay. So, and when I jump to the RF stability, and when you go to the effective lengths, you see here the effective length factor of 2, yeah? So 2, when I multiply 2 by 6, so this is the length, I have this effective length of 12 meters, yeah? And when you ask yourself, okay, why isn't it so clear? So why isn't that exactly 2? This is because of this stiffness, shear stiffness. So I go back to calculation parameters. When I don't consider the shear stiffness, so I deactivate that. calculate everything again, and then you will see the exact value of that. Yeah, let's look to the results. And now you will find the clear value of 12 and 2, because this is Euler Case 1, and there we have the effective length factor of 2. Okay, good. Another question is, if we divide the element, the buckling length will be calculated also. Yeah, that's right. You will get the buckling length to each member number. So if you divide here this length again, you will get it per member. Yeah. So you have to consider that there will be some different results. So when I divide here the member exactly at the half, now I calculate it again. You have to consider now different critical length, because here you have now 1 and 3, so member number 1 and 2, and here now effective length is 4, but the effective length is 12. Yeah, but you have a different critical effective length factor. This is something you have to consider. Good. Next question.
Next is sorry. Whether we can export or import member locations to and from Excel to or from an Excel sheet.
Yeah, that's possible. Here in the tables, you have the possibility to export or import a table. And when you want to import some of your members, you can do that here by members. Yeah, the Excel sheet should have the same structure as here in RFEM. But that's possible. You can import and export the tables here. That's possible. Another question I see, why we restrict the eigennodes to 4. What will happen if we take more? Yeah, I can show you. Maybe so. What happens if we do more? So first of all, I'm referring again to the type of model to a 3D. I delete this support direction there. Delete also this node by the help of delete node, but merge joint lines members together and make this 10 meters high. Okay. Now my load is still there. I calculate everything again. And yeah, the reason why I want to have just 4 is that when you do a stability analysis, also referring to a design standard like the Eurocode 3, only the first cases are important for your design, because when you have here the RF stability, this would be the first fail if you would have too much nodal forces here. Yeah. The second fail would be that And the other fields, like 3 and 4, they wouldn't appear because this is too unrealistic. Yeah. So this is also the reason why a structural engineer looks only the first 2, 3, 4 eigenvectors. I think at this simple structure is very clear, but if you have a more complex structure, then you should look maybe to more than 1 or 2 eigenvectors, because there can be some local problems or some global problems. When you would have, maybe I can show it here. No, this is a wrong. This is a bad example. Maybe another example. Maybe this one would be interesting. So, are there some loads? There are some loads. Okay, let's make a structural stability analysis at that case. Yeah. So I open RF stability. Sure. Okay. I open RF stability. I take load case. I consider here and 10. Okay. Calculate it. Show me the graphics. Yeah, and the reason is because I have here this one. Now I'll calculate it again. Sorry for that, because I have this one, determine eigenvector for unstable model, but I think this model isn't unstable. Show me the graphics. Okay, and here we can see some interesting things. So, okay, here we can see this eigenvector, and here we can see, okay, the deformation in the y direction is a global problem, and there I think there are some joints problem, because it shouldn't be like that. Yeah. And when we look to maybe other eigenvectors, okay, there we see, okay, there's also deformation in that positive y direction or negative y direction. And we can look also to some local problems, but I think there are just some global problems. But it can be possible that one column is maybe too weak, and this would mean that we have there a local problem. And the first reason when one column should be too weak, that we increase the size of the cross section of that. This would be maybe one solution to do that. So this would be helpful to look to more than 1 or 2 eigenvectors. Okay, good. Next question.
Yes, Daniel, we had a question recently. If we could show how to perform a load combination. I don't know if you want to show it now or perhaps in a next training.
So this will be part of the next training, but I can show you that very fast. So very, very fast. So I create here for that example a second load case. In this case, yeah, test load 2, but into another action category, in this case imposed. Click on OK. Now I put there an additional nodal force, in this case 200. Yeah. And then I create a new load case. We do it now manually. The next training, so the second part, we do it automatically. So I jump here to the load combinations. I create here a new load combination, give them the name, okay, design internal forces, and put both to that. The different partial factors are here. I click on OK. And when you look now to the load combination, you see here there's 300 and 135. And this is a load combination. Yeah. Okay, next question maybe.
Okay, how do we check? Sorry, I'm not quite understanding the question. Okay, how do we check if the joint of member is okay, and how are we designing it?
Okay, so first of all, the checking of nodes, if that's okay. You have here the possibility to make a plausibility check. This function allows you, okay, if the whole structure is modeled okay. Yeah. Also here under the tools, you have here the model check. And here you can see, for example, if you have identical nodes, so two nodes on the one exactly same place, and also some other things like overlapping members, lines, and so on. This is one thing, one way, or sorry, two ways to check the nodes and also the system. And designing joints or connections, you have to use one of our add-on modules. In this case, when you consider steel structures, you have to use, where is it? RF joints, design of joints. This would be the add-on module for designing joints here. Yeah. Okay. Next question.
Is RF stability a general add-on for concrete, steel, and timber structures? And if so, what do the RF timber and other than that? If so, what does RF timber do?
Yeah, so RF stability is an add-on module. That's right. There are different design possibilities to make the stability analysis concerning concrete, steel, and timber structures. And maybe in the steel structures, there is, I don't know the English word, I have to open it. There is one possibility to make a stability analysis with the help of the equivalent member method. Yeah. And to do that, you have to know the buckling lengths. And the buckling lengths you can calculate with the help of RF stability. And the same also with timber structures. Yeah, here at the RF timber, I think you have similar way to consider that. Here, effective lengths, members. You can put there the effective lengths. You calculate it with the help of RF stability. But normally you have to put it here manually. Yeah, but you can add that also here with the help of RF stability. That's possible. yeah, you can do that. Okay. Next question, and maybe also the last question, I would say.
Okay, if I have to give a wind load, which direction I need to select? First, local load related to true member length or global load related to true member length?
I think the best way to show that is to show that in an already existing project. So I open maybe this one. Okay, so in this case, I choose here, I create a new load case. In this case, this will be a load, a wind load. And there are several ways to put their load. For example, when I have to consider suction, yeah, or compression forces concerning the wind loads, I have to do it like that. So first of all, new member load, because these are only members. I put the wind loads, so I refer to the local related to true member length. And in this case, when I have to consider the suction or the wind pressure at their value, when I want to consider the compression wind or wind compression, I have to add the positive value. And when I want to consider a suction of the wind forces, negative, because it relates to the local orientated z-axis. Yeah, this would be the wind load. Yeah, and when I want to consider snow loads, for example, I have to consider this kind of member load. This would be the global related to true member length. Sorry, this one to the projected member length. This would be the snow load. And this is a little bit different to the self-weight. Yeah, if you have some loads on the roof, this is a little bit different. Okay. Good. Then okay, good. Okay, then I would say let's finish this training. I want to add some small information about our website. Yeah. Here in our website, you find a lot of information, especially for you as beginners or for interesting people. Here at support and learning, you find here at learning the first steps with RFEM and Airstop and so on. Also, if you have any questions concerning every topic, you can ask us without a support contract or something like that. You can ask us everything. Yeah. For that, we are here. And what I can really recommend is models to download. If you go there, you can download a lot of models from modeled with our software, and if you stay a little bit longer on one of these pictures, you can scroll, you can move it a little bit, you can watch it. This is really nice, and you can download everything. Yeah. What I can really recommend is also here the education and e-learning. Here we have our online course, RFEM 5 for beginners. It's really helpful. This is a series with 11 videos. There you can check your knowledge and so on and learn a lot of things. And yeah, you can here also download a free 90-day trial and so on. Yeah, good. Then I would say, let's finish this online training. It was what a lot of fun. It was really happy, and I hope we will see you on Friday, next following Friday, because there is the second part of our online training.
So I would also like to thank you all. It was good fun. I hope you had fun too and learned something. And hopefully we will see each other again on Friday.
Okay, guys.
Okay, so have a nice week.
Have a nice week, have a nice day, and stay healthy. So, bye bye.
Okay, bye.